continue this talk.
Thanks. Okay, welcome back. Yeah, so in the second part of the gap story, we're going to get into the more interesting case of topological states. But just to remind you very quickly, that's part one. We had this definition where I have a family of wave functions of different sizes, and if they're related in a certain way, then I call it an S-source RG fixed point. And so far we've been talking about the case of S equals to 0, where I can make the entire state at any size from a product state. And now we're going to talk about the case of S equals to 1. So here was S equal to 0, and I use this machinery of some kind of adiabatic evolution or slightly modified adiabatic evolution to construct the unitary, which maps the system at some size to some other size. And now I'm going to try to repeat this story, but for more complicated phases of matter, which no longer have the property that there is a path from the state at some size to a product state in a finite amount of time. So there's no way to deform the Hamiltonian of the toric code to reach a product state without encountering a phase transition, because we know it's a topological phase, so it has to be distinct. So how can we deal with these systems where I can't go to a product state in a single step? And the idea of the S-source RG is that I can't go to a product state, but I can go to the state of the same system at a smaller size. And that's what we'll use to construct the ground state wave function. And so the first example that I want to talk about is what I call chiral insulators. And I claim these will be S equal to 1. And what you should think here, let's just think in 2 dimensions. Think about an integer quantum Hall state, or for my purposes, a Chern insulator. And what I want to show, so I'll tell you what this movie is in a second, but the setup is that I have a lattice model of fermions hopping on a square lattice. So here's my lattice model. And at first, the red and the blue sites are all equivalent. So it's a model with 2 bands per site. There's nearest neighbor hopping. And this model has 2 bands, one of which has Chern number 1 and one with Chern number -1. So a half filling is a Chern insulator. So it has integer quantum Hall effect. And now what I want to do is I want to modify the Hamiltonian, which means I introduce this dashed bond and possibly also modify the chemical potentials on the various sites. And the purpose of this modification is that what I want to do is I want to separate out the blue sites. I want to turn them into product states. And I want to turn the red sites into a new lattice, which is rotated by 45 degrees and has a square root 2 longer lattice constant. So in other words, I'm taking a square lattice, I'm throwing away half the sites, and then the remaining sites are now connected in this way. So it's like this. Let me draw a little picture here. This is my original lattice. And now I select every other site. And I want to deform, so originally it was connected like this. Now I want to deform the Hamiltonian. So such a site here is now in a product state, and there's now a Chern insulating state on the remaining rotated square lattice. And you see the point of this is that I'm thinning out the lattice. I'm removing degrees of freedom. I'm locally turning things into a product state, but keeping the overall wave function the same. So it's still a Chern insulating state, but it's on a different lattice now with a different Hamiltonian with fewer sites. And so what I'm showing here actually is, so what we do is we have a hopping here, chemical potential here, chemical potential there. And with just those 4 parameters, so we're increasing the size of the unit cell. So we're making the Brion zone smaller. So here I'm plotting energy as a function of K. This is in the original zone, so really only half of this band makes sense. But I'm plotting now the band structure of this model as a function of some deformation path among these 4 parameters. And the purpose of this little movie is to show you that, let's wait till the start. I start here, so the bands touch, and then I slowly deform. They start to separate. And the important point is that the gap never closes. So this dashed line here at mu. It gets very small. We didn't work very hard to optimize this, but the gap does never close. There's a well-defined parameter trajectory in Hamiltonian space, which I just factor out all these blue sites. And you see that's what's happening at the end. I start out with the same band. I did form, I did form, I did form, and at some point I've managed to decouple them. They become flat, and then I can push them away to infinity. They're just a completely flat, non-interacting band, which is partially filled, so it just goes away. So I just literally remove half the fermions in the system. They enter a flat band, I can just take them away. They're decoupled, they're unentangled. And the remaining half fermions live in a turn insulating state on half as many lattice sites. And now I claim that this implies the system is S equals to 1. And the way it works is the same as it did for S equal to 0, except now instead of going from completely unentangled, I go from system size L plus product states to system size 2L. So all I do is I insert into this H of eta the path that I found in the previous slide that I showed you. You can look at our paper, there's a table with, I think, well, there's like 8 steps that you have to do, but anyway, it's a definite parameter path. And it simply maps you from this Hamiltonian where everybody's connected to a Hamiltonian half as many sites where every other site is in a product state. And so using this Hamiltonian plus the quasi-adiabatic machinery, I produce a quasi-local unitary which maps the ground state from size L plus product states to size 2L. So I've just constructed the unitary. I mean, I haven't told you what exactly it is, but I proved to you that it exists. I showed you a path in Hamiltonian space that remains gapped, and then we just use this analytic machinery to produce the unitary transformation. Okay, so the Chern insulator is an S equals to 1 fixed point. In fact, it's not S equal to 0. There's no way to go from the insulator to the trivial state because it has a Hall response. So in the language of tensor networks, for example, what this implies is that there's a tensor network, there's a Mera, which represents an integer bound Hall effect. At the same time, there's also a PEPS. And I want to emphasize one thing is that in this case, we never had to do a variational calculation. We found this Hamiltonian path. Of course, we can solve the whole problem, so it's a little bit silly. But the point is that if I have this Hamiltonian path, and this is a non-variational way to construct the ground state wave function. So I never need to solve an optimization problem on a large system in principle. If I have this path, I just build a wave function directly. End of story.
Right.
Yeah.
Does that mean that this is a long-range entanglement? Because if you imagine you have an infinite system and you do this procedure, you never actually get a product state.
Indeed.
But this integer Topological effect, is that classified by as a short-range entanglement?
Just wait. I'm going to explicitly discuss this in a little while. So yeah, according to my definition, it's short-range entangled, but from the perspective of the S source RG, it's actually as entangled as toric code. But that's actually not true in a certain precise sense, which I'll explain shortly. That's a great question. Okay. So this case has no ground state degeneracy, but it's at least has this topological property so that it can't be deformed to a product state in a single step. But what about an actual topological state? So for example, toric code or some discrete gauge theory or fractional quantum Hall states. So actually many years ago, Vidal and company and Xiaogang and I and Zhencheng and Mike Levin, we actually showed that at least in terms of the string net formulation, all such discrete gauge theories in this deconfined limit have Mera representations. That is, they're all RG fixed points. So in the language I'm using here, there is a Hamiltonian which maps from the toric code at size L by L to the toric code at size 2L by 2L. And it's not hard to write down this Hamiltonian. And it's gapped the entire way. Now, much less trivial is the case of fractional quantum Hall states. And so here, the question is, can you make a Hamiltonian that interpolates between L and 2L? And I think it's at least plausible that you can do this from the previous construction of Chern insulator. For example, take your, use the parton construction, take 3 copies of the Chern insulator, do a projection onto the SU3 singlet. That's the Newton's third wave function. This wave function comes from Chern bands which are gapped the entire way, so it's very plausible this wave function indeed interpolates between L and 2L, as we wish. But that's a little bit unsatisfying. So what we want to do is give a general argument why such states are all S equal to 1. And that led us to the idea of what we call a topological quantum liquid. And the idea of a topological just means it has some ground state degeneracy. It's sort of interesting. Quantum because it's got entanglements. And liquid because in a certain precise sense it's insensitive to the precise shape of space. So you can put it in containers of different sizes and it doesn't care, it flows. And this should be contrasted. Tomorrow I'll talk about another model called Hawes code, which does not have this property. So it depends sensibly on what size region you put it in. But a quantum Hall state is a liquid. It flows. It doesn't care about the precise geometry of space. And so a sort of hand-wavy definition of a topological quantum liquid is some state of matter which is insensitive to smooth deformations of geometry. So there's a lattice definition which is more precise, but let me just think that what I mean here is really anything with a field theory description is such a topological quantum liquid, almost by definition. And so fraction from Hall states, at least in some limit, have a field theory description in terms of their universal properties. And so we believe they're topological quantum liquids, and then we can use this deformation for the particular case where we locally increase size to show that all such field theories have S equal to 1. So to be precise, you could use a construction which we call the expanding universe construction, inspired by our own universe, where you take a metric, space-time metric, which consists of some time and some scale factor which is increasing with time, times a flat space, let's say. And as long as the quantum field theory remains gapped for all values of A, then I have explicitly constructed a path in Hamiltonian space from size 1 to size 2 just by changing A from 1 to 2. So as long as you believe that quantum field theory can be put into a sphere or a torus, and you can adiabatically increase the size of the torus without closing the gap, then you have to believe that it's a quantum liquid, and it implies it's S equal to 1. So I would say this argument, although I didn't construct the actual unitary, this argument should convince you, I think, that anything with a low energy limit, which is a quantum field theory, which is an ordinary continuum limit and is gapped, is automatically S equals to 1. So we can go and try to, we can write down a particular model and try to tune it so we can find a gapped path. But I think it's conceptually clear that a quantum Hall state has this property that it can be deformed. We believe it does, and then that implies it's S equal to 1. So if you want to make things precise, we just mean if you assume, you can easily show that topological quantum liquid implies S equal to 1. You use the precise definition, which you can look in the paper. And then we appeal to your sense of decency that most reasonable things have this property of smooth deformation. So in particular, I would say that any insulating state, any superconducting state with which is a gap, any quantum Hall state, any discrete gauge theory, any spin liquid with a gap, these are all of this class. And you can ask the opposite question. You can say, does S equals to 1 imply that it's a topological quantum liquid? And I think the answer is yes, but this is not rigorous. But the idea is the following. Suppose I give you some Hamiltonian path. So I know it's S equal to 1. So I know there's a path which takes me from size L to size 2L, which doesn't close the gap. Right? So let that path be h of eta. And now this Hamiltonian can be decomposed to the sum of local terms, each of which is a function of eta, some smooth function. But now I can imagine doing a kind of trick. I can take this purely time-dependent Hamiltonian and turn it into a space-time-dependent Hamiltonian by taking this eta and letting it vary as a function of position. So in other words, in one region of space, I don't do anything, but in another region of space, I actually make the lattice finer. I add in degrees of freedom over here. So over here I do nothing, over here I do something. But crucially, I make this deformation, this eta of x, very slowly in space. So locally, anywhere you look, if I have a Hamiltonian, and I plot the norm of these terms as a function of x, it's very slowly increasing. So if you look at any local points as a function of x, and you kind of rectify things, it looks like it's just a small perturbation on top of a uniform background. And we know that the system is stable to small perturbations. So the idea is we apply this argument locally. We say everywhere it looks like it's a small perturbation of some locally flat, some locally position-independent Hamiltonian, which we know is stable, so it's stable everywhere. So as long as eta of x varies slowly in space, and as long as there's a gap with local stability, then this Hamiltonian h tilde will also be gapped. It'll also be in the same phase as h. And the point is now that we just let this eta of x vary slowly, so we can add degrees of freedom here, take them away there, we can do whatever we want. So we can deform space locally, but the Hamiltonian stays gapped. So I think this is, it's not a rigorous argument, but in part because we don't have a good notion of local gap, at least not for this purpose. But I think it should convince you that it's possible to take any such Hamiltonian, which is s equal to 1, and turn it into a locally varying Hamiltonian, which is still gapped and stable in the same phase. And you can ask, what goes wrong if s were 2? Well, then what you have to do is you have to have some kind of like Y junction, right? You have here 2 copies of the system, then you glue them together somewhere into one copy of the system. But that's sort of weird, you know. Now it's not one copy on some locally varying space. It's one copy here and then 2 copies over here, because you need 2 copies to produce a larger system. So somehow you really need the fact that it's s equals to 1 for this argument to make sense. And so we believe, although it's not rigorously shown, that s equals to 1 implies topological quantum liquid, and vice versa, topological quantum liquid implies s equal to 1. So these are essentially equivalent concepts for this gapped case. And so the claim that I want to make then is that indeed, let's say in 2 + 1 dimensions, all topological quantum field theories are s equal to 1. Here's a kind of amusing experimental example, which I like. So I talked about expanding universe. Well, so our universe is actually expanding. Every 10 billion years or so, it doubles in size. And QCD is a quantum field theory with a gap. And the gap does not close as a function of time. Pions don't suddenly become massless. So apparently there is a path in Hamiltonian space of QCD, which goes from system size L to system size 2L in a time which is of 10 billion years. And thus QCD is s equal to 1. Okay. What about what? Well, I think it's trivial. It's just 1. But actually the point is it doesn't matter. It could have degenerate ground states, and it's the mere fact that this path exists, experimentally it exists, implies QCD is s equal to 1. So QCD could have some hidden topological structure that we don't understand, but apparently it's s equal to 1. It could be what?
5 million years ago, there could be a phase where we don't know today.
Yeah, but I don't understand the point. But right now, there's no. I mean, you don't really believe that QCD gap is going to close when we get to like 20 Hubble radii, do you? No, I mean clearly it won't close. That's. I mean, if we know anything in the universe, like we know that. Pretty sure. Okay. Yeah, so this is a little tongue-in-cheek. But I strongly believe that QCD is S equal to 1. And I think this is actually not a terrible reason to think so.
I can relate. Can you, for my sake, so can you show a slide to define S again?
Yeah, sure. So here's a picture in 2D, right? So it just means that we take one copy of the state. So like take the QCD ground state on 100 by 100 lattice, and then for every site of that lattice, put in 3 blue sites, if it was 2-dimensional. So just make it make it from 1 to 4, and then apply a local unitary and make it on a 200 by 200. Say what?
Wait, you're just saying that doubling the system size does not change the ground superiority.
Yeah, for this model it does not.
Yeah, I don't see how that QCD example actually convinces that. Actually, you don't know what happened with the already has some example. It's not adiabatic evolution expand size of the system.
No, I'm not talking about, it doesn't have to be real-time evolution. It just means that there's some path in Hamiltonian space which is gapped. I mean, it's not necessarily real-time evolution.
Yeah, so when you say unit expansion is experimental observation, we are only observing very, very short time period.
Sure, yeah.
How do you know for that entire time period there's nothing significant changes in the spectrum?
In the spectrum of QCD.
Yeah. How do you know that?
Well, the proton has not become massless over the short time we've observed it. That's what I mean by experimental evidence.
It's a short time, right? You're talking about 10 billion years.
Yeah.
I don't know if you observe far galaxies,
Yeah, that's a good point. I mean, if you the spectrum of radiation from sodium that we see from some distant star proves, or is strongly suggested that.
Exactly, yeah. To make your point, we have to make sure that we are observing the entire evolution to make sure there's nothing changing. Right? So, I mean, observing very galaxy far away, that could be a way to do that. But without observing very high, very long time, I think we cannot make a statement. I mean, we cannot make an
Well, I emphasize it's partially a joke. So don't take it. I mean, okay, but it's not a joke in the sense that I'm 100% sure. I'll bet you any amount of money you want that QCD is S equal to 1. You can make QCD from size L to size 2L on a torus without closing the gap. I'm certain of that.
Yeah, I'm also certain of that, but experiment don't have nothing to prove that.
Yeah, it doesn't prove that. It suggests that.
So you are saying that in the QCD case, there are no range entanglements, right?
Yeah, I mean, it depends on what you mean. So QCD viewed as a theory of a fixed cutoff is actually a trivial state. We believe it's a trivial state. It's actually S equal to 0. But because the correlation length of QCD is so long compared to the microscopic scale, whatever it is, it's better to think of QCD as almost critical, in which case it would have to be S equal to 1. So all field theories where you take the cutoff sort of to infinity, take it away, they should all be thought of as S equal to 1, even if they eventually have a gap. Because most of the RG flow is some sort of CFT that goes on forever at the top. But yeah, I mean, if you had an actual lattice gauge theory with some fixed cutoff, and you fix the cutoff and you take the system size to infinity, it's S equal to 0. At least if it's in a traditional strong coupling phase. So yeah, I'm not claiming we know exactly what the phase, well, I'm claiming, okay. But yeah, I think whatever QCD is doing, it's a gapped thing. Maybe it has topological degeneracy, maybe it doesn't. But it appears to have this property that you can expand it without closing the gap. Certainly as a quantum field theory, as a theoretical model, it has this property. Whether the experimental universe has this property is indeed open to question. We only have a small window in this. But as a quantum field theory, it has this property, certainly. Now, the non-joking part of this is that, from the point of view of numerics, this may be a useful tool numerically. Because, of course, it is interesting to try to calculate the spectrum of QCD. calculate ground state properties of the string tension, for example, or the pion mass by looking at the decay correlations. And so, as it stands right now, this is by no means a competitor to Monte Carlo, but perhaps in the future, if we develop this technology enough, this actually provides a way to access QCD, even with fermions, even with dynamical fermions. Because it doesn't matter if you have fermions. Fermions are fine. It's still S equal to 1. So even with dynamical fermions, it may be possible some years down the road to actually beat or complement what can be done with quantum Monte Carlo, especially in the case where you have dynamical fermions in the game. Right? So in principle, the ground state of QCD is, I think, something that's you can calculate efficiently, in quotation marks, meaning in polynomial time and some refinement parameter on a classical computer, which is not something we knew before. We, the quantum Monte Carlo takes exponential time if you have dynamical fermions. So maybe not right now, but perhaps one day this could be a significant part of the simulation of QCD. And it's sort of also interesting, if you like money, to think maybe with some effort, with much extra effort, you could actually also win $1 million by proving that the ground state of QCD is gapped. But you have to work a lot harder than this. But it is at least a different way of thinking about the problem. Okay. One nice theorem we can prove, as I mentioned already, is that any S equal to 1 fixed point and D greater than 1 obeys the area law. So this is the theorem. And it's a nice theorem because it's very general. And if you believe, for example, that all gap field theories are S equal to 1, then it proves that all field theories obey the area law. And this is a... Yeah, this proves actually true for anything with S equal to 1. And in fact, yeah, I don't assume gap to make this proof. So far, I've assumed the gap to show you that there are many systems which have S equal to 1. But tomorrow I'll show you gapless models with S equal to 1. Okay, so this is the kind of thing which is of interest to people in quantum information, with quantum Hamiltonian complexity, where they like to prove area laws from minimal assumptions.
How about like Fermi?
Well, Fermi liquid does not obey the area law.
Yeah, so it's not S.
Yeah. Yeah. It's, so, in 2 dimensions it's S equal to 2, and in 4 dimensions S equal to, 3 dimensions S equal to 4. I'll explain that tomorrow. Or at least we believe it's that. And in fact, as I'll discuss towards the end of tomorrow, actually we have a more general argument in this paper for the area law for more general kinds of theories. And I'll talk about that tomorrow, which include theories with higher S. So now let me wrap up today with a discussion of short-range entanglement. And so, okay, we've been sort of struggling a little bit with how to define short-range entanglement. So I say there's definitions. There's East Coast definition, because Xiaoyang is on the East Coast, which says that short entanglement means that you have a short circuit, a finite depth circuit that creates the state from a product state. Or you have a quasi-local unitary or whatever. They're essentially equivalent. Then there's a West Coast definition, because Kataev is on the West Coast, which says there are no anyons, no topological entropy, and so forth. And the important, well, it's not that important, but a minor wrinkle is that they don't quite agree. There are states that this says are short, that this says are long. The example being integer quantum Hall, for example. So our definition that we came up with, we sort of thought of this independently for various reasons, but then realized that Kataev and others had something similar, although it's not published, is we say a state is short-range entangled if it has what we call an inverse state. So this actually sort of meets the concept of invertible topological order that Xiaoyang talked about yesterday. And the idea of an inverse state is that we say a state psi has an inverse if there's another state psi inverse, such that the product of the two can be deformed with a local unitary into product states. So what does this mean physically? It means you can't take an integer quantum Hall state to a product state, but you can take integer quantum Hall plus its conjugate, and you can take that to a product state. Right. So short-range entanglement means not that you can make the state